Welcome to the deep dive, where we really try to cut through the noise and pull out what matters so you walk away truly informed. Today, we're plunging into one of the most exciting and, let's be honest, challenging frontiers in computing: quantum. We're going to explore a really groundbreaking leap, something that could get us significantly closer to building practical, powerful quantum computers.
Yeah, it's a fascinating area. The promise of quantum computing is just immense. We're talking about machines that could theoretically solve problems that are just completely intractable for even our best classical supercomputers today.
Right, things like breaking modern encryption, you mean, prime factorization and all that.
Exactly that. Prime factorization, but also tackling complex linear systems or simulating quantum chemistry in ways we just can't dream of classically. Think designing new materials, new drugs.
And we have seen some pretty incredible progress already. I mean, we have these noisy intermediate scale quantum computers, right? The NICE-Q machines.
That's right, usually around 50 to 100 qubits. And they are doing fascinating experimental work. It's a really vibrant field.
But the key word there, as you mentioned, is noisy.
High noise levels, limited qubits. And that fundamentally stops them from running the really deep, sophisticated algorithms we need for that transformative quantum speed up everyone's chasing.
So the ultimate goal then, the sort of holy grail, is the fault-tolerant quantum computer, an FTQC.
Precisely. These are machines where the quantum information, which is incredibly fragile, is protected. Rigorously protected by quantum error correction.
Like a self-healing mechanism built right in.
You could think of it that way, yeah.
Yeah.
But even within FTQCs, there's a really stubborn bottleneck. Some operations, the Clifford gates, they're relatively easy to do fault-tolerantly, like the basic quantum arithmetic.
Okay.
But others, the non-Clifford gates, are notoriously difficult. The T-gate is the classic example.
And you need those T-gates for universal computation to do basically any calculation.
Exactly. They're essential. And that's where this technique, magic state distillation, or MSD, comes in.
Ah, okay. So if the non-Clifford gates are the tricky special operations,
then the magic states are like the super high-quality fuel you need to run them. MSD is how you prepare these incredibly high-fidelity magic states.
got it. And that leads us to the core problem this new research is tackling, the overhead.
Right. Conventional MSD, the way it's usually done, operates on logical qubits, information that's already been encoded for error correction.
Okay.
And that leads to what they call large spatiotemporal overhead. Basically, it needs a huge number of physical qubits and takes a lot of time. It's a major bottleneck for scaling up.
And today we're looking at a brand new approach, something called zero-level distillation.
That's the one. And it sounds like a fundamental shift, not just a small tweak. The insights today come from a paper titled Efficient Magic State Distillation by Zero-Level Distillation, just published June 20th, 2025. Researchers from Osaka University, Riken, and Fujitsu.
So our mission for this deep dive is to really unpack what this zero-level distillation is, how it works, and why it might be such a big deal for actually building these powerful quantum computers.
Okay, so we've set the stage. Fault tolerance is key. Non-Clifford gates like the T-gate are essential but hard, and you need these magic states to make them work reliably. But let's unpack this. Why is it so difficult to get these magic states in the first place? You mentioned the overhead, but what's the core issue?
Well, the magic states are needed for something called gate teleportation, instead of doing the difficult non-Clifford gate directly.
Which is error-prone.
Exactly. You prepare a very high-quality magic state, and then you use a simpler fault-tolerant operation involving that state to achieve the same effect as the difficult gate. The problem is, preparing that initial magic state to be high-fidelity enough has been incredibly resource-intensive itself.
And traditionally, that involved operating on logical qubits, which you said causes this massive overhead. Why is that so inefficient? Think about it like this. A logical qubit is already made up of many physical qubits, right, to protect it from errors.
Right.
Conventional MSD takes these already encoded logical qubits and tries to distill them further to improve their quality for magic states. So you concatenating codes, you're adding layers of protection on top of protection before you even start the distillation. It just requires an enormous number of physical qubits and tons of operations.
Okay, I see. It's like building a protected vault just to polish something inside it, which then needs another vault.
That's a good analogy. And this new approach, zero-level distillation, tries to avoid that entirely.
By doing the distillation first at the physical level.
What's fascinating here is that this isn't just an incremental improvement. It's a fundamental shift in where this distillation happens. Zero level means it happens entirely at the physical level.
Yeah.
using the raw physical qubits directly to prepare, ultimately, a high-fidelity logical magic state.
So you clean up the ingredients before you put them in the fancy packaging, basically.
Exactly. It leverages a known technique, nil-at-all dot type distillation, but applies it using the steam code, which is a 7-qubit error-correcting code. And the clever part is how they map this whole process onto a practical square lattice architecture, the kind you see in many superconducting quantum computers, with error detection built in.
Okay, so you distill physically using the steam code. Then what? How does that state get used?
Good question. The distilled magic state, now encoded in the scene code, is then transferred. It's either teleported or converted into surface codes.
Ah, surface codes. We hear a lot about those. They're good for fault tolerance on these 2D chips, right?
Very much so. Rotated or planar surface codes are very promising, robust choices for FTQCs, especially with superconducting qubits. So you're transferring the high-quality magic state into the format needed for the main computation.
And the initial promise, what's the big takeaway?
The headline finding is that this zero-level approach can be more efficient than even sophisticated conventional methods. It cuts down significantly on both the number of qubits needed, space, and the time it takes.
Which could make building these things feasible much sooner.
That's the hope. It lowers the resource barrier quite dramatically.
Okay, this sounds really promising. Let's get into the nitty-gritty. How does it actually work? You mentioned a teleportation-based approach first.
Right. It involved 3 main processes. First is encoding and preparation. You start by encoding a magic state into the steam code. Initially, this isn't fully fault-tolerant. It's still a bit noisy. At the same time, you prepare a very specific helper state, a 7-qubit cat state.
A cat state. Like Schrödinger's cat.
Sort of related conceptually. It's a state where all 7 qubits are linked. They're all zeros or all ones simultaneously in superposition. This particular state is useful because it works well with the limited qubit connections on a square lattice.
Okay, so you have your noisy steam-encoded state and your cat state ready. Step 2.
Step 2 is the distillation via Hadamard test. This is the actual purification step. You use the cat state to perform a Hadamard test on the steam-encoded state. It's basically an error check. You measure something, and if the parity of the outcome is even, you keep the state. If it's odd, an error was likely detected, and you reject it, start over.
So it filters out the bad attempts.
Precisely. And while this is happening, you also prepare another necessary logical state, the plus A state, using the rotated surface code. That's needed for the next step.
Which is step 3, teleportation with lattice surgery. Sounds intense.
It is pretty clever. Lattice surgery is a technique where you merge the steam code, holding the newly distilled magic state, and the surface code, holding that plus A state temporarily.
Like connecting 2 grids.
Kind of. You perform a specific joint measurement, a logical ZZ measurement, which effectively transfers the quantum state information. Then you split them apart again. Crucially, during this merge and split, certain error checks, called Z-stabilizer measurements, have to be done twice. If the 2 measurements disagree, it signals an error, and again, you reject the outcome.
Lots of checks built in. And then you finalize the teleportation.
Yep. After the split, you do more stabilizer measurements on both codes. And finally, you measure the steam code qubits directly in a different basis, the X basis. These measurements complete the teleportation, moving the high-fidelity magic state onto the surface code, ready for use.
And you mentioned this is efficient in terms of the actual operations?
Remarkably so.
Yeah.
It only needs single qubit gates, measurements, and 2 qubit gates between adjacent qubits on the square lattice. Very practical. And they use a smart trick for moving qubits around 1-bit teleportation instead of swap gates, which is slower and add more errors.
Keeps the circuit shallow, you mean? Less time for errors to creep in. How shallow are we talking?
Really shallow. Only 25 steps, physical gate operations for the rotated surface code version, and just 23 for the planar surface code. That's very low for this kind of process.
Okay, and the output is a D3 surface code state, but you said they expand it?
Right, D3 gives some basic error correction, but for longer computations, you need more protection. So the D3 state is then fault-tolerantly expanded to a larger code distance, like D5 or D7. This builds in more robustness against errors accumulating later on. Now, besides that teleportation method, they also came up with an alternative, direct code conversion.
Ah, okay. So skipping the teleportation part, how does that work, and what are the pros and cons?
Exactly. The main advantage is resource savings. You don't need to prepare that second logical state, the plus CO state for teleportation. So it uses fewer qubits overall, which is great.
But there must be a trade-off.
There is. The circuit depth is higher. It takes 42 steps instead of 25 or 23.
Almost double. And more steps usually mean more chance for errors.
Right. A deeper circuit means qubits idle longer, potentially accumulating more noise. So the logical error rate ends up being slightly higher with this method compared to the teleportation one.
So how do they actually convert the code directly? If you're not teleporting, how do you change it from Steam code to surface code?
It's a process of careful deformation. After the magic state is distilled in the Steam code, they use a sequence of these one-bit teleportations and stabilizer measurements again. But instead of teleporting the state out, these operations are used to gradually change the structure of the code itself. Think of it like reshaping the boundaries in checks. It morphs from the 7-qubit Steam code through an intermediate 6-qubit code structure and finally settles into the rotated surface code structure.
Wow. And presumably error checks are happening throughout this morphing process too.
Absolutely. Multiple error checks are embedded. If stabilizer measurements give conflicting results at any stage, the whole thing is rejected. It ensures that only states likely to be correct make it through the conversion.
Okay, the theory sounds solid both ways. But you said the proof is in the pudding, or the simulations. What did the numbers actually show? Here's where it gets really interesting.
Yeah, this is where it gets exciting. They ran detailed numerical simulations using tools like QualAX for full vector simulation. And they were smart about it, using optimization tricks to simulate circuits needing maybe 40, 50 qubits with only about 20, 23. Makes these complex tests feasible.
Right, and they use a standard noise model to make it realistic.
Yes, the standard depolarizing noise model. Noise applied after gates, noise during idle times, with a physical error probability P. It's a good benchmark.
Okay, lay the numbers on us. The logical error rate PL, how much better does it get?
The key finding is that the logical error rate, PL, scales roughly as 100 times P squared, 100 P2.
Okay, P squared scaling is good. That means errors reduce quadratically. What does 100 P2 mean in practice?
Let's take an example. If your physical error rate P is 10.4, one error in 10,000 operations, which is ambitious but achievable, then PL becomes about 10.6. One error in 1,000,000 operations. That's 2 orders of magnitude improvement.
Wow, okay, that's significant. And if the physical errors are higher, say 10.3?
Still a solid improvement. At P equals 10.3, PL becomes around 10 to 4, so 1 order of magnitude better, still very valuable.
And did the different methods, teleportation versus conversion, give slightly different numbers here?
They did, consistent with the circuit depth. Teleportation to planar surface code was about 93 P2, and to rotated surface code, about 106 P2. The direct code conversion being deeper was slightly worse at 199 P2, but still that P2 scaling is the crucial part.
Right, still a big improvement over just P4. What about the success rate? How often does this distillation actually work and not get rejected?
It's actually pretty high. At the higher physical error rate, P equals 10.3, it succeeds about 70% of the time.
Yeah.
And if you can get your physical error rate down to P 10.4, the success rate jumps to 95%.
That's great. Means you don't waste too many cycles attempting distillation.
Exactly. It's efficient not just in final error rate, but also in producing the states reliably.
Yeah.
So if we connect this to the bigger picture, this work isn't just about a single improvement. It's about fundamentally rethinking how we build and scale quantum computers.
Right. Let's talk implications. What does this mean for the near term, for these early FTQC systems people are trying to build now with limited qubits?
It's almost perfectly suited for them. Conventional multi-level distillation is just off the table for these early systems. Too many qubits needed. But zero-level distillation has this incredibly small qubit footprint. The spatial overhead is roughly just 1 logical qubit's worth of physical qubits.
So it's practical now.
It's practical now. And even though the 100 P2 error scaling isn't theoretically the absolute best possible scaling like P4 or P8 from higher level schemes, its low resource cost makes it the viable option to actually get started.
And what kind of computing power does that unlock for these early machines?
Well, achieving that logical error rate of 10^6 with P10 for physical errors is considered good enough for what's called megaquop scale computation.
Mega quantum operations per second.
Sort of, yeah. It signifies the ability to run pretty deep algorithms. We're talking maybe tens of thousands of these tricky rotation gate operations. That pushes capabilities way beyond what current NISQ machines can do. It really helps bridge that gap.
Okay, that's the near term. What about the long game? Full-scale FTQCs. Does zero level replace the conventional methods eventually?
No, and this is really important. It combines with them beautifully. You can use zero-level distillation as the first stage. Follow-up work has already looked at this. There's something called 0+1 level distillation.
Zero level feeding into level 1.
Exactly. Use zero level to produce decent magic states, then feed those into a conventional level 1 distillation protocol. This combined approach achieves an overall error scaling of OP6. That's incredibly powerful suppression of errors.
Whoa, p to the sixth power, that crushes errors down fast. What about the overhead then?
Well, one study showed you could get up to 6 orders of magnitude improvement in the logical error rate for the same resource cost compared to just level 1. Or, looking at another way, to reach a target logical error rate like 1016, which you'd need for really huge problems. This combined approach could reduce the total resource cost, space, and time by about two-thirds.
A factor of 3 reduction in cost and time. That's enormous for scaling up.
It really is. And there's also that other related idea you mentioned, magic state cultivation.
Right, inspired by zero level.
Yes, it uses different codes, color codes, at a physical level, also aiming for better scaling, achieving OK with some clever tricks. It suggests reducing the space-time overhead by potentially 2 orders of magnitude to reach a target error rate. So zero level isn't just one technique. It sparked this whole new direction of thinking about physical level processing for error correction.
Wow, what a journey into the weeds of quantum error correction, but with such important implications. So, to wrap up, zero-level distillation is this major innovation, right? Doing the magic state preparation efficiently, right down at the physical qubit level on a practical chip layout.
And with substantially reduced qubit numbers and overhead compared to the old ways.
And we saw those really compelling numbers improving the logical error rate by potentially orders of magnitude, high success rates, shallow circuits.
That 100p2 scaling, the 70-95% success rate, and that low depth around 25 operations, all very practical figures.
And critically, it's not an either thing. It works with the existing roadmap for fault tolerance. It helps near-term machines get going, and it slots into the long-term plans to make full-scale quantum computers more efficient.
Absolutely. It's a key piece for both stages.
So what does this all mean for you listening in? Well, imagine a future where these incredibly complex problems, things we can't even properly tackle today, become routine. It's innovations like this, like finding ways to distill quantum states right at their foundation, that might unlock those possibilities. This deep dive really shows how pushing efficiency at the most fundamental level can open up entirely new doors.
Which leaves us with a thought. What other big bottlenecks in building these machines might have simpler, more direct solutions if we just rethink them from the ground up? Are there other things we can do right at the physical level that we haven't considered yet?